Welcome! In previous clips, we have shown how water can be stored in two types of aquifers, unconfined and confined. In this video, we focus on the first type. Unconfined aquifers develop when the uppermost part of the Earth's subsurface is formed by permeable rocks. Water from precipitations infiltrates the ground, is blocked by an impermeable layer, and starts saturating the permeable medium. At the same time, water will start flowing downwards towards the discharge domain, establishing a steady-state situation. As a result, the upper boundary of the saturated layer, called the water table, lies within the permeable medium itself. This is different from confined aquifers. From the drawing, you can also see that the unconfined aquifers are in direct contact with the surface of the Earth, with all the activities which take place there. In the schematic cartoon, you can see in more detail the main elements of an unconfined aquifer. You see the permeable upper layer, loose sediments or rock, underlain by permeable lithologies. With the onset of precipitations, you see the water flowing downward and laterally, and the resulting water table situated in the permeable layer. Note that in the scheme shown in the slide, the water table intersects the topography at the level of the river, which means that the water will flow from the aquifer into the river. The river is a discharge zone. Quantifying and managing water resources stored in the unconfined aquifers is only possible if a correct map of the water table is done. To construct such a map, piezometric wells are typically drilled in the area of interest and positioned on the topographic map. From these wells, the height of the water level with respect to a reference level is measured and plotted on the map. Eventually, contours are drawn to interpolate between the data points. Let us look at a somewhat more realistic water table map. Here, you see the topography of the area. Along the section AB, to the right of the map, you see the topographic profile we will look at. A number of wells have been drilled in the area, and the position of the water table with respect to the reference level has been determined. Eventually, contour lines are drawn. Projection the position of the water table along the AB section on the altitude plot, you see clearly that the water table is not flat and is generally higher in correspondence of the relief rather than in the depressions. The water table intersects the surface at the river floor and in correspondence with the small lake on the right-hand side of the profile. We conclude that these water bodies are partly fed by the unconfined aquifer. With this kind of maps, you will be able to predict the position of the water table in other localities of the map, for instance, where people want to build a house. The position and topography of the water table will remain constant as long as the geometric and physical properties of the subsurface remain constant and, more importantly, as long as the recharge and discharge also remain the same. If this is not the case, then very important modifications affect the system. Imagine, for instance, a situation where precipitation increases significantly. This will lead to a rise in the water table, and areas which were previously just above it will be flooded. In times of decreased precipitation or increased extraction, the water table will descend. This has a number of consequences. For instance, deeper wells will need to be made, and water bodies, such as rivers, which act as discharge areas, will start charging the aquifer, with water moving from the river to the aquifer itself. The third relevant consequence is land subsidence. Water removal will allow further compaction of non-lithified sediments, resulting in subsidence at the surface of the Earth. The engineers building the Leaning Tower of Pisa were apparently not aware of the consequences of extraction of water for the city. I'd like to conclude this clip with a great example of how people thousands of years ago had understood unconfined aquifers and figured out how to use the non-horizontal position of the water table. People in many countries, such as Iran, had realized already that the water table had a slope and was higher towards the recharge areas in the mountains than in the low domains. They started then digging horizontal tunnels from the flank of the mountain to the interior of the mountain, of the hill. Once they hit the inclined water table, water started flowing, bringing life to the previously dry region, allowing human settlements and agriculture. The underground tunnels were then equipped with vertical shafts and other infrastructures. These systems are called cataracts. In some places of Morocco, there are tens of these tunnels feeding communities and their activities. Having looked at unconfined aquifers, we turn now our attention to confined aquifers. These form when waters infiltrate the ground in a recharge zone, enter a non-horizontal permeable layer, which is bounded by impermeable lithologies and which plunges into the ground steeper than the topography. As a consequence, water will flow along the deepening layer and eventually form an aquifer, which, beside in the recharge area, is fully disconnected from the surface. Eventually, water can reach these charged areas, such as some rivers, or be pushed to move upward through the nearly impermeable layers as shown in the slide. In the slide, you see now associated water table which forms the upper boundary of the unconfined aquifer, and we'll drill into it. Now, you can also see the confined aquifer. A well targeting the deeper confined aquifer will traverse the low permeability aquitard and eventually reach the aquifer. At this moment, something unexpected occurs, namely that the water in the well will rise far above the top of the aquifer itself. These are called artesian wells. Clearly, a behavior very different from that of the unconfined aquifers. This shows that the confined aquifer is under pressure and that it has a strong hydraulic head. In some cases, water might even come at the surface, forming a kind of fountain. In the latter case, we speak of a free-flowing spring. Connecting the piezometric levels in the different wells, one defines a potentiometric surface. As you can see in the example in the figure, this surface can be above the ground. Including the same kind of measurements for a region, you can build a map of the potentiometric surface. This is a key document to predict flow patterns in the deep underground. To further discuss key phenomena associated with confined aquifers, we will make the example of the Dakota aquifer, one of the largest aquifers of the world. A schematic and vertically exaggerated geological section is shown now in the slide. Note that the Dakota sandstone outcropping in the Black Hills, dipping to the west and flattening the central part of the basin. Sands are sandwiched between less permeable layers of shales and other Paleozoic rocks. The recharge region of the aquifer, we said, is the Black Hills in the west of South Dakota. Here, waters infiltrate the ground and follow a few major aquifers composed of porous sands. These aquifers are continuous for hundreds of kilometers and lie at depths of hundreds of meters in the east of the state. Agriculture is of great importance in South Dakota and in most of the central US, and a huge amount of waters have been pumped for irrigation. The consequences are clearly seen when comparing the potentiometric surface in 1909, for instance, with that of 1940, when the water table was at places hundreds of feet lower than at the beginning of the century. The lowering is obvious and has sparked large discussions and worries on how to better manage the badly needed water resources. Note also that because water flow is slow, stopping does not lead to an immediate improvement of the situation, and substantial time will be needed to return to a substantial, sustainable level. Similarly to, and probably more than what we have seen for unconfined aquifers, further important consequences of overpumping is land subsidence. When the sands of the aquifer are water saturated, the water exerts a pressure on the grains, which keeps them somewhat at distance from each other. When water is extracted, then the grains will move to a better compaction, producing land subsidence at the surface. As you can see from the measurement on the pole, water in the agricultural region of the San Joaquin Valley has descended by tens of feet within 50 years as a consequence of over-extraction. Confined aquifers are great opportunities because of the large amount of water they host and because contained waters are often of good quality. There are, however, challenges, some of which have already been mentioned. In the next clip, we expand these topics. Welcome. In this third clip of the hydrogeology block, I want to briefly mention 3 hydrogeological case studies. I do this to address a few major challenges associated with water exploitation and with your future work as geologists. These challenges refer to phenomena taking place in the coastal domains, to the hydrogeological consequences of long-term changes in the amount of precipitation, and to the interactions between water flow and pollution. I'm sure that quite a lot of you live in areas where one at least of these challenges is real. The coastal domain is a region where fresh water, typically carried by rivers, come in contact with marine waters. Because of its low density, fresh water will tend to remain close to the surface and will overlie the body of marine waters, which is characterized by higher density. The 2 bodies of water will be separated by a relatively thin transition zone. The position of the fresh salt water transition can be clearly defined, for instance, by measuring chemical elements such as chlorine in the underground waters. On average, besides smaller seasonal oscillation, the position of the fresh salt water contact is fairly stable. At longer timescales, that of tens of years, things might be different in relationship with decrease in precipitations predicted by some climate change models. Not surprisingly, human intervention can have a major impact on the position of the transition zone and therefore on the quality and quantity of water supplies in the coastal domain. If much more water is extracted than what can flow into the aquifer, then the water table will descend, and maybe more importantly, the fresh salt water transition will rise and eventually might reach the bottom of the well bore. Salt water will start entering the well. And this is not the end of it. The entire sediments around the well bore will be polluted by salt, making it difficult to have clean water again, even in the case that pumping decreases. Absolutely not a remote possibility, as coastal domains host, for instance, some of the largest cities in the world. We have seen in previous clips that the climate we enjoy at present is a very different one from the one dominating the world something like 10,000 years ago. In areas such as North Africa, precipitations were more abundant and giraffes and other animals were less scarce than at present in mountains like the Hogar and Tassili massifs. The waters have been flowing along excellent aquifers such as that in the Nubian sandstones and are now abundant in the subsurface of countries like Algeria and Egypt. Indeed, plans have been made and partly implemented to tap into these huge amounts of high-quality waters. The Great Man-Made River Project is one of those. Clearly, these are phosphorus water, which implies that the aquifer is not being recharged at rates that they are extracted. This has sparked many discussions, but how long will it take to cause a significant decrease? If this is in the order of hundreds of years, is it acceptable, seeing also dramatic present-day challenges? A further and very exciting feature is related to the consequences of the low sea level present during glacial times. Fresh water was then carried by waters across large portions of the future continental shelf. When sea level rose, the coastline retreated, leaving a lens of fresh water underneath the shelf. In the example of the New Jersey coast, gives you the idea of the large amounts of fresh water involved in this process. Pollution is clearly one of the major threats to the quality of our water supplies. Contaminants can enter the groundwater from point source, such as leaks from tanks, to non-point sources, such as landfills. Contaminants may stick to the grains, remain in the groundwater because they flow less easily. On the other side, flowing has also the positive effect because it allows filtering of the waters, especially if flow is slow enough. This is an effect exploited among others in the Netherlands, where water is pumped in sands in the dunes north of Amsterdam and then extracted clean and nearly ready to be used. Herewith, we have come to the end of the clips dedicated to hydrogeology. This is an exciting science and one of great social importance in which geologists will play a great role.